Dear students, please sit down. This is the time for starting our last lecture for today. I highly recommend you to come here because after this lecture we will have a test about this lecture too. So today I'm glad to introduce Andrey Kuznetsov with a lecture about the principles for customization, industrial generation, generative design. Andrey, thank you.
No, it's okay. I don't know at what distance I should stay that it should work. Like this. Then I take this. Okay. Hello, everyone. I'm glad to see. I wanted to say so many people, but I see that some places are missing. So, however, people are coming. Okay. Today. First, I would like to introduce myself because I'm not sure that most of you are familiar with me, or maybe some of you should be familiar, but more or less. My name is Andrey Kuznetsov. I'm leading currently a lab in Andrey, Artificial Intelligence Research Institute of Sber, actually, and at the same time we do in our lab. The lab is named Fusion Brain, and we do research in generative AI in different streams. So we develop and research such models like multimodal perception models. We also develop models for generating multimedia content. And I was one of the founders of Kandinsky models, which are currently the most well-known, I think, models for text-to-image and text-to-video models in Russia. And some of the models were open-sourced and were quite popular, and also submitted and used in the diffusers framework. In this year, I started a lab in Innopolis University for multimedia, for multimodal models development and design in industrial tasks. And today's talk is actually correlates with tasks in construction and in industry where generative models and generative AI can be helpful. It is actually a common question when a lot of lectures and talks about generative AI models and different models for synthetic of content are given, and people ask, what for do you need generative AI models? How can you sell them? How can you use them in real life tasks? And actually construction and industry are very good topics where generative models can be useful. And today I would like to share some information about our research and about the challenging tasks, the limits of generative models, and the complexity of some problems. So when we speak about generative AI, we mean that we have a number of generative models, like large language models, visual language models, the models for synthesis multimedia content, like Kandinsky, Veo, and so on. And we want to apply them to generate and optimize different architectural and constructional tasks. When we speak about constructional or architectural tasks or industrial tasks, we mean two types of problems. The first type of problems concerns the specific data formats that are used in these fields. Because every industry has their own proprietary formats of data for protection, for commercial protection, and for security needs. However, inside, these companies provide access to these formats, and we can use them to operate information that is stored inside companies. And the second type of problems concerns the process flow. Yeah? So when we take any industry, we have a lot of processes that have specific input and output format that are connected, and this sequence of processes gives us the final result. So, for example, in the beginning we have a technical document with description of the task of the problem, and at the end we should provide some technical schema or some report or some document that contains information about how to construct, for example, some part of device or something like this, or how to create a building, how to construct a building in real life. And all these documents, they are generated now using manual operations. So a lot of engineers, a lot of project institutes with thousands of specialists are working and trying to do this to do this in real life. They do a lot of manual operations, and the level of automatization in construction and in architecture and in industry is very low. So even if we take very well-known software like AutoCAD, like Revit, and even the Russian software like Compass 3D, we see that most of this software is very well automized simple operations, which are implemented by specialists by hands. And we want to minimize this, and we want to use generative AI for these tasks. When we speak about the motivation of the generative design and generative models that can be used in the design purposes, we understand that in the global paradigm, in the global horizon, generative models will be continued developing in the next 5 or even more years. And we see that every year a lot of new approaches, new models, new architectures are designed for text generation, for image generation, and so on. And of course, all these models, all these architectures, they have their specific limits, they have their specific advantages, disadvantages, and some of them can be applicable in real-life tasks. Some of them are more about academics and academic experiments, and we need to find out this good place in this selection, in this variety of models, to select a good choice, to do a good choice. Next, when we speak about people and specialists who are working in the field of industry and construction, of course, when it is manual work, then there should be some percentage of manual errors, manual mistakes. And of course, when we speak about automatization of some processes, we think that this can lead to minimization of the number of errors in these fields. As I already said, a lot of companies have their own internal data formats and their internal data storage of different data, different projects that they realize, that they implement. All this data is hidden inside companies, and we need to find out a way to provide them some open source vision, some usage, not to be useless, and to be quite good for implementing some complex tasks. When we started to analyze this topic of generative design, we started to develop this field in January, actually, of this year, with a bit dive in November or October of 2024. We started to find out what information we can find about generative AI or AI instruments that can be used or can be applied for the tasks of construction. And we found a report of Autodesk, and there is a link on the bottom of the slide, which took more than 5,000 participants of the survey, which were asked several questions about the applicability of AI and their interpretation of AI instruments, and the vision of how these AI instruments can be used in their specific tasks solution in the following years. And as you can see here, among participants there were architects, engineers, constructors, and different specialists. There were people from design and manufacturing, and at the same time from media, marketing, and entertainment. And most of them from 60 to 80%, believe that AI instruments will add creativity. Yeah, they will help make and solve specific problems and improve the speed of solution of these problems. And they will be useful in the horizon of 2-3 years. This is quite an optimistic view from my point of view, because these people are looking from the side of the industry, but I look at this problem from the side of researcher, and I see that 2-3 years is very optimistic when we try to find out how current big models like Quen, like many other models can be used to solve problems with specific data formats. The industry interest is can be shown by 2 quotes that I found in this report. And one of them, which was given by the CEO of International Consultants for Design and Engineering, that AI can automate many tasks and free up creative people to focus on what they do best. This is a good approach, and actually when we speak about automatization, we first concentrate on improving the speed of specialists and to remove some routine operations from their life. If we mean generative AI, and if we apply generative design and generative AI models for manufacturing and for construction tasks, we can find several benefits. Some of them I already fixed when I started my talk. So first, we want to increase the variability and creativity of design ideas. This is more about visual design, more about perfection, and trying to use several, for example, images of several projects, several good projects as conditioning to generate a big variability of similar projects. And this is what we can use for synthetic data. The next one is optimizing the design process and reduce the project development time. The average construction process, the average construction life cycle of a common building in Russia takes from 5 to 7 years. And from this 5 to 7 years period, nearly 4 years takes the document construction design. So a lot of engineers, a lot of project institutes inside developer companies, inside construction companies are doing projects. They are constructing the infrastructure of the building, they create the building model, they do a lot of research in how it can be sold after construction, think about financial risks, and any other risks that can be applicable. And all this information is done by hand, and all this information leads to a very long construction process, or pre-construction process, if we mean that construction is just a physical development of the building. The next benefit is automating the search for the best solution according to different constraints. When we speak about construction and industry, there are a lot of government documents that contain information and different restrictions and limits of how each operation can be made. In every country there are some specific documents, specifications like GOST, SNIP. I don't know actually how it is in English or other language, but however, these are just standards that provide information of how the industrial process should be organized. And there are a lot of limits, there are a lot of constraints here, and some of them are contradictory. So when we take some federal law, when we take some local law and try to find out how they can be used together, we can see a lot of contradictions. And we can use generative AI models to help constructors and to help engineers to solve these contradictions when we do the projects. Because when engineer doesn't use this information from some specific standard or he forgot about it, or he just doesn't know some update of this federal law or some federal document, then his construction, his project will be rejected by the commission, and he will need to do updates to this project, which also takes time, and all this iterative process will take time and extend the life cycle of the process that concerns the project development. The next benefit is reducing human mistakes. I think it's quite obvious. The next one is quick adaptation to changing norms, rules, restrictions, and actually it concerns, it correlates also with my previous point. And all of this actually can be combined to reduce financial costs of the design process, because financial costs, it's about time, it's about salary for constructors, for engineers who do iterative work about the project improvement and so on. And all this leads to financial and time costs decrease. In our field, we have several teams that work on these types of tasks. Here we can see that several production or industrial or R&D teams and research teams are combined to solve problems in two fields, in construction and in computer-aided design or in engineering. Here you can see the Fusion Brain Laboratory, the Spatial AI Group, and two teams about Kandinsky and Kandinsky 3D in Sber. When we speak about generative design technologies, we can take such a map of approaches that exist nowadays, and they can be grouped actually in two main groups: the classical AI approaches and the modern AI approaches. When we speak about classic approaches, here we can see genetic algorithms, some particle swarm optimization, expert system, fuzzy logic, and so on. So it's just classic ML, I think. And when we speak about machine learning approaches and generative AI, here we can see RNN, CNN, generative adversarial networks, transformers, diffusion transformers, and so on. And all this help us to work with the long context, with the generative tasks for image generation with a lot of constraints and so on. However, even Autodesk continues their research in automatization, but it is not implemented in their software occasionally. However, one of their works that was quite interesting for me last year, it is called Tile GPT, which combines approaches from classical AI method group and modern AI methods. So it is a combination of transformer and of transformer architecture and genetic algorithms for optimal arrangement. It's like wave function collapse. So the idea is that we want to generate a plan of constructing a territory which is divided into several types of objects. There can be blocks for buildings, blocks for roads, for trees, and so on. So it looks like Minecraft or something like this. And every type of blocks has different types of rotations on different positions that can be useful. For example, for buildings, there can be a straight part of the wall, there can be a corner, there can be a main wall, or there can be some dividing wall inside the building. And every type of blocks has their different positions, different ways of putting them in the project. And the idea that they developed, they used transformer as an architecture that can generate in autoregressive format, step by step, a picture actually. So it's just a picture which contains different types of blocks inside this picture. It looks like, if you're familiar with the first image generation architectures, DALL-E, which was actually based on transformer architecture, and step by step, every patch of the image was generated in this way of interpretation. And this is the same actually. But here, every patch is a type of block. So here we can see that on the second stage, the transformer is able to generate us a small map where each page, each token is correlates with some type of block. And then we use genetic approach to make a specific position of this type of object in this position. And this is how, if we speak about ground, it's okay, like trees, it's okay, but when we speak about buildings, we need to find out, using genetic approach, the architectures in such a way that the building should be closed. Yeah, there should not be different doors or different empty spaces and so on. Or the corner should not be outside of the building; it should be inside, and so on. And this combination provides a good approach for generating maps of construction for some local region, for example, in the city. So this is the field in which Autodesk does research in their field. Now I would like to go deeper in what we do, in what we develop, and what tasks and what problems we try to solve. We also organize the specific group in the laboratory that does research specifically in generative design in terms of construction. So when we speak about construction, there is a major problem that we do not have data sets in open source. We do not have any benchmarks. We do not have any metrics, but we have a problem. Yeah, we have a problem that we want to automate the process of generating content for industrial tasks, generating projects. And here, a classic approach. So we need to find out the data sets. We need to think about it like how we can how we make this data, synthesize it using big models like ChatGPT, DeepSeek, Qwen, and so on, Gemini. We should select the architecture which can be useful for these purposes and think of it like of an inference paradigm or maybe some way of supervised fine-tuning or reinforcement learning in online or offline mode and so on. And at the same time, we understand that when we speak about construction tasks, we have a lot of physical problems, physical limits and constraints that should be also involved in the architecture process. Maybe this can be put as a number of limits if we speak about coder, for example, code generation networks, or this should be a specific part of a loss function that can be used to analyze is the project is well on the step of validation or it should be corrected. So there should be some solvers anyway. And the evaluation, when we try to find out if the project is correct, we need to think of a metric or a number of metrics or maybe some QA tests. So anyway, and the first stage of developing and constructing the models or the construction objects concerns the developing of BIM model. BIM is building industrial information modeling. So this is a common format of objects in construction industry which contains information about the construction itself, the infrastructure, all the IoT devices, for example, that can be put inside the building. So this is like a digital twin in a common format, but it has its own specification. And here we can see a number of problems which I already discussed, and I do not think that I should put a step here. However, there are a lot of problems, and the goal is to speed up the design process. And here is the map or the chart of dependency between expenditure and level of influence on the stage of developing. So the first stage that is selected here with color contains high expenditure This is the conceptual design process, but it is very low in terms of cost. So it doesn't cost a lot, but it takes a lot of time and a lot of importance of everything to be correct here, because all the mistakes, they will be as a result on the final stage of construction, when fixing these problems is very difficult and is very financial costly. When we speak about B-model design, we need to find out what type of data and what type of format is used inside. And here is a sample of a project and a small part of the internal representation of this project in the Autodesk or in some software. So it is just a number of symbols, a number of classes, and their positions inside. So every point contains the type of the class, the type of connection with some other points, and different numbers, different values of floating point numbers that contain information about position in 3 dimensions. It is already called Industry Foundation Classes, IFC format, and is actually fully manual managed by experts, by constructors. So they open the software and try to create this project from the very beginning, from the foundation and so on and so on. Some of them can use some predefined templates that appear in their specific experience and use them, for example, for some default operations. But however, this is a blank page problem. Yeah? When we start to create a project, we have a typical technical document. For example, I need to create a 5-floor building for 500 people living in it. And using this internal simple representation of the technical document, the project institute takes this as a technical document as a task and tries to solve it. So when we go inside this model, we can see that actually this is a graph representation. It can be represented as a graph with a lot of connections and a lot of elements inside. And here you can see how these graphs look like for quite simple objects. So there is a bridge, a simple bridge, and a one floor, single floor house. So the graph looks very difficult. And it is not applicable in terms of any language model just to operate with this as a single file. So when we take it as a text input, it will fail, obviously. So further, we need to think of how this can be implemented, for example, through code representation. Because LLM Assistant, with this labor-intensive technology and this labor-intensive file format, type of data, they are not correlate very much. So LLM as an approach is not very useful here. At the same time, we see that the BIM representation, BIM, has some hierarchical structure. It has some inheritance of parameters and different levels of inheritance inside. And every small change in these parameters leads to updating the whole model. And we need to recalculate all the solvers that check the model, check the validity of the model to find out that it is working okay. It is also low adaptable because changes are made quite slowly, and new design requirements, when we get them from different documents and federal laws, they should be implemented here quite fast to correct the project. And at the same time, one person who is working with the project, single person, single engineer, doesn't know all the information about the project. So this is why when the project is developed, hundreds of people are working on it. So it's not about 1 or 2 specialists, but a lot of people are working on specific parts of this model design. So here, when we speak about specific people, specific roles, we can implement it as a stage work, as a specific agent who can work on code level or on text level. On our side, we developed the model that is based on multi-agent representation, which is based on the text-to-beam model. I will show a bit later. We implemented new types of roles. We updated the way of communication between these agents, because first we tried to find out the way of how to use existing architectures in inference mode, and do not trying to add hard pre-train, hard additional training, supervised fine-tuning, because the lack of data is a big problem, even when we find partners and communicate with them about data. So we speak about IFC as a core of the construction process, and we try to find out two ways of problems that we want to solve. The first problem is a help for constructors, for engineers, to find out and to answer questions about the IFC structure. We can calculate some statistics, some information about the model. We can help to find out some specific places in the model that are not correlate with new updates, for example, in the federal law. And the second type of problem is generating from the blank stage. So we have a task. We want to generate the code that can implement this task. And working with the code is a good solution, because for IFC there is an IFC framework which is quite well developed and updated in the GitHub. And it is a way of interpretation of the model through the code sequence. And actually code is a good way of, a good medium way for coming to different other modalities. And this specific data format, like BIM model, is a good way of interpreting it through the code sequence. The multi-agent architecture inside this approach contains several roles, and each role does its specific tasks to create finally the project itself. So here we can see, it's not very good scene, but however. So the first role is the architecture. The architecture takes the technical task and tries to divide it from the point of architecture, what types of the project should be implemented to construct a building and to create a project finally. Then we have the product owner, the man who combines two expertise, the expertise of engineering and the expertise of data scientists or IT specialists that implement the model finally. So when we speak about our approach, about our process, and when we mean that BIM model or IFC model for us is just a code structure, just a code implementation, we need to find the connection between the tasks of IT specialists and the tasks that are given by architectures. So the architecture divides and says we need to construct the building in such a form with several floors, with several flats on every floor, with a specific distance between flats and so on. And then after that, the product owner provides a more technical way of interpretation of this task to the IT specialists. And this is the third role here. This is the role of programmer who writes a code and generates the code implementation of the task. And the fourth role here is the reviewer. It's on the bottom of the slide, which checks the model, which runs several solvers in the computer-aided design software. And these solvers check the model and give their output on the validity of the model. For example, they check if the model is correct in terms of geometry, in terms of the landscape, in terms of different physical conditions and constraints and so on. And when this reviewer receives these outputs from the solvers, he gives some combined report on the correctness of the model. And if there are some mistakes, then this report is going inside to the programmer, to the IT specialist, who checks the code and updates it with conditioning on these mistakes. Several cycles, several iterations of this reviewing and coding, and we receive a result of more or less similar to the initial project. So here we select several prompts, like 10, 12 prompts, 10, 20 prompts, and they are very different in the form of the building, in the number of floors, and so on. But actually, it cannot be called a benchmark or something like this, because it is very small and is not standardized in terms of the task. So on this point, we see the structure, and we want to implement the structure for building different blocks. So here is how the module in the Revit works. So we just implemented a plugin based on this approach and installed it in the Revit software, which is the most common software that is used by the architects and engineers. So here we can see that giving an input textual task, we receive a code block that is implemented further as a building. And here we can see that not only the geometry correlates with the task, but also when you see afterwards in details the presentation, there is also the material of the walls. There are also different metadata parameters of the walls. All of them are here. And further, we can use additional instructions that can be used to update or to edit the project. We can move different parts of the project. We can add specific objects. For example, like here, we can add a roof. But we should find out and we should fix that it is not a one-step operation. So we can not solve this in single shot or single way operations. We need to find out a specific implementation. And what I write here, like add roof or fix roof size, is just a simplification of how the prompt looks like and how it describes the task for the model to correct the building model. Going deeper in terms of hierarchy of the tasks, the next task is generating the floor plan. Here, the main idea is when we have a border or some limit of some square, of some plan in the building, we need to find out the positions of different zones in the room. So where should be a bedroom, where should be a guest room, toilet, and so on and so on. And here we also have a lot of constraints that go not only from our perfection or for our representation of the visual design or the interior design or the planning. We also see here a lot of restrictions in terms of documents, federal documents, and all the standards that give us an ability to understand that while constructing, we need to put specific rooms not connecting with each other. For example, we cannot put a toilet inside the bedroom, for example. However, some people like these ideas, but in general way, we should find out a common interpretation of the rules and different limits that should be applied during construction. The goal for this is to generate an apartment or a floor plan according to several conditions. So we're going to set up a task for diffusion models for diffusion generation. And here how it looks like. There are some data sets, some data that can be used for training that contains information about the apartment structures and their division on different types of zones inside the structure. And here we see that when we take diffusion models, we can put a JSON representation of some part of the of the apartment. We can describe it as a JSON format and use it in a denoising process to generate the similar picture or the similar vector representation of the picture when we want to make it similar to the some visual representation. So describing it as a code or as a JSON or any other format in the middle of this process, we can train the model to find out the best solution for generating such type of content. So this is a quite an obvious representation of the diffusion training task, diffusion model training task. And at the same time, we also see that there is some adjacency graph connection between different rooms. Because when we describe the task, we want to find out, we want the model to find out the best solution according to our request. So several rooms, the number of rooms, the square of specific rooms, the connection between different rooms. So all of these limits and constraints should be validated during the generation process. However, in terms of data science task, it is quite a simple representation where we have the fixed input, which is textual interpreted or code interpreted, and we have the visual output, so conditioning and so on. And we did this research. We implemented a model and trained it on several data sets, including pre-trained or including proprietary data inside that can be used to generate different ways of apartments and using external boundaries. We can generate the adjacency graph from the textual description and then generate high quality vector layout for the flat. Now we try to move from this representation to the more general floor plan, not only the apartment plan, but the floor plan in general. And the third task concerns implementing the visual design. Here we go deeper in this hierarchy of tasks and go inside generating the plan, the layout of the plan, where different types of furniture, different types of interior design are put as a different colored squares here on the picture. And using this as a condition for the image generation models, like Flux, like Kandinsky, like many other models, we can generate a top view of the interior design. This is also a very interesting task, because here we can use different limits and different constraints that can be interpreted as an instruction from the user when he wants to generate a design for his specific conditions. And here is a small example of it. So in zero shot, no models work with this. So it is very difficult because when the models are trained, they use general data, but here we speak about very specific representation of the data. It's a top view. And most of the models, I think practically all of them, they are not able to generate this specific view. However, they try to do this. But even when we do specific keywords in the instruction, we get not a good result. The next step is 3D visualization. It is also quite understandable. So we use the two-dimensional picture as an input and generate three-dimensional scene. Combining this with some shops, which provide pictures of some specific elements in design, we can cover the layout of the interior design with some specific objects from the shops. So finally, we receive the plan and the cost, the financial document that can be used for economic estimation of the interior design in the room that you want to apply. Okay, this is speaking about construction. So as you see, three types of tasks, like BIM modeling in general, like floor plan generation or apartment generation. And the next one is interior design visualization. So different types of generative AI models help to implement this. But more or less, they are not working in zero shot. They are working in quite interesting schemes of communication and with additional fine-tuning in some ways. And Kandinsky 3D, it's just internal model for generating three-dimensional objects in STL format and in other ways of visualization. So the next task concerns computer-aided design in engineering and manufacturing. And here I would like to start with the task itself. So one of the most important and valuable tasks in engineering is the reverse engineering. The idea is that construction of some complex some complex parts or some complex devices is very difficult and takes much time for implementing when we speak about generating some specific element in a big device. We need to have not only the three-dimensional model, but we also need to have a lot of technical documents that are generated by this model. And in real life, the process looks as follows. For example, some complex device is broken. It is unmounted. It is divided into internal parts. So it's deconstructed. We find the place of error, so the broken device, the broken element, and give it to the three-dimensional estimation. So there is a specialist which comes with a hand 3D scanner and evaluates all the point cloud of some object, of this broken object, for it to be further reconstructed and re-implemented in a three-dimensional model in the CAD software. Here we can see that the process takes time. It takes a lot of time to generate the three-dimensional model, and I show further why it is difficult. And at the same time, we have a lot of problems when we use 3D scanning. First of all, 3D scanning cannot see all the holes, all the elements inside some device, and there are some losses in the point cloud. And when the engineer takes this point cloud as the input, he needs to check all this information and to validating it, to reconstruct it as a good model, reconstructing the operations that are needed to create this model or this element. And finally, we see that the surface is quite structurally constructed in comparison with the point cloud that we receive on the left. So on the left, there is a point cloud that is received for general, quite general elements in different devices. At the same time, in real life, we can receive the elements like this, like it is shown on the left. So we see that there are a lot of broken elements, and we need to reconstruct them to create from this complex broken element a correct element that can be produced further on the manufacturing stage when we give it from engineers to manufacturing. Speaking about the current state of academic research, it is a bit better in comparison with construction because there are benchmarks, there are data sets for training models, and there are even some baseline approaches that can be used as a baseline for comparison. Some of the benchmarks of the data sets, they contain information in synthetic format, so it's just synthetic details. Some benchmarks contain information from real life, so it is very much dependent on the type of operations and the type of data that is stored inside. Because, for example, a small comparison between academic data and real life data is that in academic data sets, the points in point cloud data, they are not a floating point, they're just integers. But when we take the information from the real life, we get a lot of floating point information. So training on synthetic, on academic data sets is not a good way for implementing it in real life further. So this leads us to the task of generating synthetic content. However, at the same time, we are not able to use real scans because they are not applicable for training. And as I already said, there are a lot of problems during scanning, which cannot be fixed during or afterwards. So we cannot, actually we can create different scans of one device, of one element, but we are not able to combine them in easy way. So here we can see that different limitations in angles of scanning makes it available to give a full representation of the model. And at the same time, the operations and the complexity of the operations that are used for restoring or reconstructing of the models is not fully provided in academic data. What does it mean? It means that when we take the point cloud, the images of some element, we want to provide a number of operations in the CAD software sequentially, which gives us the final model. So these operations are usually oriented on some geometrical or physical operations, like extrusion, like revolving, sweeping, shelling, and so on. So all these operations, they in combination may give us some final element, final detail that we want to put in production on the manufacturing stage. First, some of the operations are used very frequently, some are used more or less frequently, and some of them are very rare or like singleton, so used single time in 1,000 or several thousands of operations. It means that if we want to reconstruct most of the models, we need to train the model that is able to use input like point cloud, images, textual description, and give the output as a code representation for at least two operations, like evolving, extrusion, and revolving. And this gives us also a good approach. There are also some enhancing operations, so shaping and enhancing the shape, like holding, chamfering, and so on. There are two approaches existing. The first one is based on diffusion models. So we have the input CAD command structure on the stage one. It's the top left of the slide, which is using tokenizer, is represented at the latent code. And this latent code is a fixed representation of the code structure. Further, we have the geometry. We have the input of some three-dimensional models that is correlated with this CAD command structure. And we use a frozen geometry extractor, geometry encoder, to encode this information and to provide another implementation, another latent representation of the geometry. Further, it can be distilled, and we can remove several types of geometry representations and use only single one on the bottom row. But this is another stage. Distillation is just done after the training of the whole model. After that, we take the latent code of the textual description. We add, in terms of attention, the information about the latent representation of the geometry, and try to train the diffusion transformer denoising operation just to create a new view of latent code to find out how this latent code can be generated by using only visual representation, and finally receive the latent code that can be used for the CAD recoder on the first stage to reconstruct the number of operations, the sequence of operations and the operations themselves in this diffusion-like process. Further, the authors add some DPO fine-tuning to fix complex operations, but it looks like this. Another approach is based on multimodal LLMs or VLMs. More or less in this way, they can be used as a one term. Here we also have several types of encoders. We have adapters. We can have tokenizers for specific code structure. And our idea is to use large language model as a decoding mechanism to reconstruct the code structure. And this is how our model Kadril appeared. This is a model that we released, I think, a month ago or something like this. It combines the architecture of the multimodal research that we designed, and also improved by the online GRPO modifications. So here we can see the point cloud input, the images of the element that we want to reconstruct, and some text representation, some technical task that is written in a simple textual form, so it's not a code structure. And at the output, we see the cat query code that is written in Python, and this decoded code can be used to visualize the device that we want to generate. Now it contains only one operation extrusion, but we are working now on improving the number of operations that can be used for generating different elements and to be used in real life. Also trying to generate some additional information in ChatGPT and other networks and other solutions for synthetic content. In comparison with existing models, we see that there are models that are trained on different number of data sets. DeepCAD stands for D, and CAD-Recode dataset stands for R here. And the subindex here means what types of internal data we use. So there are point clouds, there are images, text information, and this is how they are divided. And we see that our model in this setup of multimodal implementation, so here we can see that in the top part of the table, there are a lot of models that are using in training data only point clouds or only images, so some specific modalities. But Kadril, using two types of modalities, leads to better quality and gives state-of-the-art metrics on most of the data sets, on most of the benchmarks for most tasks. It is a very good result, and it also gives us an ability to find out how a combination of different visual modalities can give impact on the final result. So sometimes it is called an emergent capability of models, or the transferring approach, when we take two types of knowledge and combining this knowledge, which are more or less combined in visual representation but are not combined in the architecture. This gives us a very good improvement in terms of quality. And taking another data sets like CAD-Recode, which is correlated with the same title of the model itself, CAD-Recode, we see that improvement that was done by GRPO modifications gives us much better results in comparison with the baseline model. When I said about synthetic approach, I meant that we can take some big model for generating. We can generate these cat query operations. When we give an input, give some condition like seed primitives, and try to generate similar models, similar reconstructed models in terms of operations, giving some samples as a good examples. Now we try to improve the training data set here. And here we can see that this solution, this iterative solution of generation, provides us new parts or new pairs of parts for the dataset for training. So we have the description of the model, and at the same time we have the visualization of the model. Here we can see some synthetic data samples. These are models that are quite rare, can be used in real life, but they represent different combinations of operations that are also very useful for training the model. Because when I showed previously, there is a number of shaping operations and enhancing operations, and combining them in the different sequences, in the different orders, with different number of quantity of these operations, they may give us some very specific forms of objects that further can be used for training and for fine-tuning on the GRPO, for example, stage, or even just fine-tuning. However, when we speak about cadre code or similar models in terms of reverse engineering and creating assistants, we know that there is a hype nowadays about creating assistants for different specialists, and we want to use the model as a heart for assistant and create and work with it in assistant mode, because adding textual information inside the cadre or any other model gives us an ability to use it in chat mode, for example. So we can generate a chat communication. It can be iterative, and if we have a long context or a long context with some additional data storage or memory, like RMT, like REG technologies and so on, we can extend the possibilities of the solution. So the assistant in this representation, in this type of seeing the task, gives us actually a way of presenting the way of improving the model in real life, or using the model in real life. So this is how academic research can be implemented in real life for some specific tasks. And here we can see that using software for generating, like Autodesk, like Compass 3D, we can use it for generating models, extending it and exporting it as a DSL code, for generating design of the elements. Then we can use instructions for this, and all this regulatory rules, documentations, governance information, and so on, just to use it as a specific condition for generating the models that we need to generate for reconstruction. And in general, if we speak about computer-aided design, there are several types of agents that can be used for engineering tasks, design engineering, as I showed before, and even process managing. All this information can be combined in a general assistant mode, where large language model can be used as a connection for not only different types of data or different types of modalities like point clouds, images, and so on, but also as a mechanism for interpretation of this information, for working with code, and for combining, for creating combination between tasks for communication. Because single operation or single tasks that are solved by the models or the architectures that we design is just a technical solution of the task, but we need to also correlate them, put them in one communication mode. So, speaking about the next steps or the ways of solution of the task that we described today, the first one concerns creating benchmarks and metrics, and especially it is important for construction, where the data, there's a lack of data, but we try to solve it, and also synthetic content can be helpful. The next task is just an engineering task for developing plugins to provide a test access for engineers to receive feedback, so to generate like RLHF but in real life with real tasks, and to improve transferability of our research to real needs of production stage. We also want to set up and to use all our expertise in multimodal research, in multimodal architectures design, and apply all our knowledge about LLMs and VLM models for critics, for real-world tasks, for generating solutions and improving the speed of different operations, and also find out some new ways of implementation or some new ways of using these architectures for production. And of course, creating AI assistants. Actually, all of these tasks, they contain not only engineering problems or engineering challenges. All these engineering challenges contain a lot of academic research and a lot of academic stuff that should be involved to solve the problem effectively. And now we are looking for improving the team, for finding new specialists to do this research and to be on the border between research and production. So we'll be glad to answer your questions and discuss the problems afterwards. Here is the link on my Telegram channel, on the Telegram of Andrey. So thank you very much. The end of the day is a bit sleepy, yeah?
I'm here. Thank you for the talk. So, yeah.
Oh, yeah.
Thank you for the presentation. I wanted to ask about the CAD drill results. Like, what was the main drawbacks of this method? Why these metrics are not still ideal? What are the problems?
Thank you for the question. Actually, the main problem is the academic benchmark itself. Academic benchmark is not showing the real problem of the reconstruction. Because reverse engineering is settled on the base of a lot of real-life problems that are very difficult to generate in once again, like this. It's very difficult to create such cases and to generate them to be implemented in real life. Of course, this is a very complex case. Of course, there are more simple cases. But however, the academic benchmarks is more about understanding the task, not understanding the real task, but just understanding how to solve the problem. But when we put it in real life, the real engineers take our model and they laugh. Okay, we can now make a hole in the metal element. So what more? What more can you do? And of course, we look at this, and this is a challenge for us because the next level of complexity of reconstruction of such models will lead us to better understanding of the real life tasks. And this is the key problem now. So benchmarking is good. Academic research is good, state-of-the-art papers, CVPR and so on, so good, but most of them are not applicable in real life, and we want to make a bridge between these tasks.
Thank you.
Thank you for your lecture. I also have a question. Can you please tell me if you tried and your team tried to use just open source LLMs to generate the CAD query code, how they are performing, then they need to generate some complex designs, not the simple ones?
Thank you. The main problem for them is that they are not, it's quite a simple interpretation of the answer. They are not very good with the numbers. Yeah, when we give their technical description of what element you want to reconstruct, with a lot of limits, with a lot of numbers, with a lot of specific floating point parameters that should be used when you reconstruct, they fail in most of the cases. So they understand the task. They understand that you want to create, for example, a solid metal plate with 5 holes, but 5 is not implemented. So it can generate 4, 6, 8, 2, 3, so how it looks like. But it is not correlating with the initial task. And this is just a simple operation. But when we speak about extrusion, revolving, and so on, most of the cases it fails. So this is the problem of the general context and the general knowledge of the model, but not the specific knowledge. And this is why additional modalities, they give additional limits, additional conditions for decoding, for autoregressive decoding.
So even the reasoner model struggles with math.
Yeah.
Have you tried to use agentic frameworks?
What do you mean agentic?
I mean,
Like length chain, like this one?
I mean to use just a few large language models with very simple tasks to improve the math solving, etc.
There is also a limit in complexity. So for some tasks, they are able to solve this problem, but when we have several models on inference stage, it is quite cost inefficient. When you have several rows of thinking, you have several versions of re-implementing the model. Of course, it can do, but it is very, very costly.
Yeah, thank you very much.
How hard would be to adapt this framework for some specific conditions like construction, like in permafrost areas in the north of Russia, or in some other kind of emerging conditions or old conditions, but very specific?
This is actually a stage for research now when we work with additional documents and the restrictions and limits and constraints that can be from different documents. When we speak about physical conditions, it is much more complex. I think we need to think of, and I've seen some ideas about this in some papers, when we improve the loss function with additional physical constraints, that can be implemented as a specific part of the loss. And this can lead for better physical understanding of the task. Maybe this will help. Especially for physics-based or physics-oriented models, this can be useful, I think.